Okay, so now we're going to go over some Laplace transform examples. Now, we have five over here, and just because these are the common ones, we will practice on the most common ones first. So we have t cubed. We don't have to apply the definition. We can actually just use the shortcuts. 3 factorial divided by s to the 3 plus 1, or 6 divided by s to the 4. That's okay. E to the 3t is 1 over s minus 3. Now this is not necessary for us to add the condition. We kind of take it for granted that it's true, but it is important that we do so regardless. Sine of 4t. The Laplace transform of this is 4 divided by s squared plus 4 squared, or when simplified, s, or 4 divided by s squared plus 16. So that's okay. Let me circle this. Let me circle this. And then just to kind of hit the point home of the fact that Laplace transform, because it's defined by an integral, is linear, we have three terms here. And we can easily find their Laplace transform pairs. We have s divided by s squared plus 5 squared. Apologies if s looks like a 5 here. It's meant to be a 5. Plus 2 times 2 factorial divided by s to the 2 plus 1 plus 1 over s minus 3. Notice that regardless, each part is kind of treated as its own Laplace transform, and we just kind of combine them together. So when simplified, we get s divided by s squared plus 25 plus 4 divided by s cubed plus 1 over s minus 3. So that's okay. Now these Laplace transforms, because they are part of the common Laplace transforms, and the viewer is free to verify that these are in fact of exponential order, we can understand that these integrals therefore have valid Laplace transforms. Now, I want to bring your attention to one that doesn't have a valid Laplace transform, and I want to kind of show you why it doesn't have a valid Laplace transform. So the last problem is e to the sine of t. I mean, e to the at has a valid Laplace transform. That's okay. Sine of t, or I should say sine of bt, has a valid Laplace transform. But what about when you combine one into another? Does this have a valid Laplace transform? Well, let's check. The two conditions that we must meet is 1, exponential order. The first one is in the case that e to the sine of t has to be less than or equal to some kind of constant m, which we'll just say is 1, times e to the ct. Now, there is no way to relate sine of t to c of t exactly. We can do it maybe approximately, and perhaps it'd be valid. But in this situation, we want to show that it's entirely valid in the first place. Well, I mean, one thing we could try for the viewer is to do a Taylor series expansion. So what we could do is note that this is our Taylor series for sine of t to the 2n plus 1 divided by 2n plus 1 factorial. So what this tells us, we have t minus t cubed over 3 factorial plus t to the 5 over 5 factorial minus t to the 7 over 7 factorial. And if you and I were immortal, we could go on forever. We could keep writing as many terms as we like to demonstrate our point. But because you and I may not be immortal, we will just write this. This is O of t. This is some kind of tail term. What this essentially tells us is there are a lot more terms, but we don't care about them. We only care about maybe up to 4 of them, and we can just call it a day. So when doing this expansion, we have e to the t minus t cubed divided by 3 factorial plus t to the 5 over 5 factorial minus t to the 7 over 7 factorial plus some tail term that we don't care about, being less than or equal to, or rather it should be less than or equal to, e to the ct. Now, using the property of exponentials, where exponents in the power that add together multiply in the base. So we have e to the t, e to the negative t cubed over 3 factorial, e to the t to the 5 over 5 factorial, e to the negative t to the 7 over 7 factorial, and e to the O of t, which we don't care about, e to the ct. Now, if you want to kind of do an apples to apples comparison, let's say that c was equal to 1. If this was true, this and this goes away. So we have e. Now, just to kind of save us some time, let's call this k1 and then k2. Or sorry, let's use it. So let's do it this way. Let's call this n1, n2, n3. And then this is maybe nk, for example. So we have n1, n2, n3, yada yada yada, nk being less than or equal to 1. Now, if time was equal to 0, this would be valid. If time was equal to anything else, like really 1, for example, it doesn't work anymore. So it fails the first condition. And we can check the second condition, but already we can see that it fails. And because it fails, e to the sine of t does not have a valid Laplace transform. So it has no valid Laplace transform. Now, maybe approximately, it could have a Laplace transform. If we kind of consider that time is maybe really small, then we could probably do that. Except even then, that argument is invalid because we're integrating from 0 to infinity. And infinity is not a small time. So we are led to the conclusion that this has no valid Laplace transform. Now, for the viewer, I challenge the viewer to see if the following one has a valid Laplace transform, and if not, why not? T to the t. Next time, we're going to be talking about other Laplace properties, as well as just formally what they're called, and we can wrap it up by talking about the applications of Laplace. Okay, thank you.